Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, and in this video I would like to invite you to observe the solution of 15 questions on power circuit analysis that frequently appear in exams for electrical engineers. Let's go to the first exercise. Let's go to exercise number 1. A 10 kVA 20 kV three-phase generator has reactance in per unit equal to 0.1. This generator is integrated into a system whose base power is 100 kVA and whose base voltage is 40 kV. Therefore, what is the value of its reactance in per unit at the basis of the system? Alright, my friends, this is the exercise. Let's go to the solution. The exercise provided this information for the generator and for the system. What we need to understand first is that this value of reactance was calculated based on these base values of power and voltage. What we need to do is to convert this into these new base values of power and voltage, okay? And this is what we are going to do. We are going to carry out base conversion. We know that for any given equipment or system, the reactance in per unit is equal to the reactance in ohms divided by the base reactance of that specific zone or that specific system, okay? And we are going to relate this system to this system here. Imagine that this system here is system 1 and this system here is system 2. So x PU2 is going to be equal to x divided by x B2, okay? Under any given system, the value of the reactance in per unit is equal to the value of the reactance in ohms divided by the base value of the reactance in that specific region or specific system. Okay? We are doing this because we want to install this generator in the system here, and to do this we need to work with another reactance. This is the reactance based on these base values. We want to use this here, but we will not use 0.1. We need to adjust in order to fit the new system, okay? The reactance in per unit is equal to the reactance in ohms divided by the base reactance of the system. Okay, my friends? Observe here that this x is common to both expressions, and we are going to use this to come up with the expression that's going to enable us convert from one base to another. Okay, my friends? So x is equal to xPU1 times xB1 which is equal to xPU2 times xB2. Okay, my friends? This expression is going to enable us calculate the new value of the reactance in per unit. And in this way, xPU2 is going to be equal to xPU1 times the base value of region 1 divided by the base value of region 2. Okay? But observe that x B1 is equal to the voltage squared divided by the apparent power of that region, and similarly xB2 is equal to SB2 squared divided by SB2. We are going to substitute these values here to find the final expression that will enable us calculate what we want. And then from this we get that x pu 2 is equal to x pu1 times vb1 over vb2 squared times sb2 divided by sb1. All we need to do now is to substitute the values. We need to substitute the values to find what we wish, as pu2 is equal to 0.1 times 20 kV divided by 40 kV, okay, squared, because VB1 is 20 kV and the VB2 is 40 kV. And now the powers SB1, SB2 is 100 kVA and SB1 is 10 kVA. And then the value of the reactance when the equipment is installed in another system, in this case this system here, is 0.25 per unit. Okay, my friends, this is all the exercise requested of us, and let's go to exercise number 2. Let's go to exercise number 2 now, my friends. For a three-phase electrical power system operating with an unbalanced load, the currents in the three phases are 20 phase 0 degrees, 10 phase negative 60 degrees, and 10 phase negative 300 degrees respectively. Therefore, calculate the positive sequence component of the current in phase A. Alright, my friends, this is the exercise. Let's go to the solution. We have to understand what the exercise wants. And the exercise wants the positive sequence component of the current in phase A. Okay, my friends? And this is the information that the exercise provided, and it is enough to calculate the positive sequence component of the current in phase A. Okay? The relationship between the currents along the cables and their symmetrical components is IA, IB, IC is equal to 111 1A squared A 1A squared I0, I1 and I2. Okay, this is the relationship between the currents along the cables and their symmetrical components. But this expression is not going to help us much, because it helps us when we have the symmetrical components and want to find the currents along the cables. We want the opposite, we want the symmetrical component. Then we're going to use the inverse of this expression. We're going to use that I0, I1 and I2 will be equal to a third of 111 1A squared 1A squared A IA, IB and IC. Okay? And in this way, if we already have the currents along the cables, we can calculate their symmetrical components. Alright, my friends, using the aforementioned information, we will be able to calculate the positive sequence component of phase A. And bear in mind that A is equal to 1 phase 120 degrees and A squared is equal to 1 phase negative 120 degrees. Alright, my friends, we wish this. We wish the symmetrical, the positive sequence component of the current in phase A. Then it is gonna be I1 is gonna be equal to a third of IA plus AIB plus A squared IC. Okay? A third of 1 times IA, A times IB, A squared times IC. Okay? This is simple matrix multiplication, and substituting the values, we find that I1 is equal to a third of 20 phase 0 degrees is the current along cable A, plus A is 120 degrees multiplying IB, and IB is 10 phase negative 60 degrees plus 1 phase negative 120 degrees multiplying IC is equal to 10 phase negative 300 degrees. 10 phase negative 300 degrees, okay? And now it is simple mathematics. If you know how to operate with complex numbers, you are going to discover that I1 is equal to 10 phase 0 degrees amps. Okay, my friends, this is the answer of this exercise. This is the solution. Therefore, the value of the positive sequence component of the current in phase A is equal to 10 phase 0 degrees amps. And this is all for exercise number 2. Let's go to exercise number 3 now, my friends. Exercise number 3 now. A single phase power supply network feeds a load by supplying 1 kVA of apparent power to it, which has an inductive power factor equal to 0.76. Capacitive compensation was applied so that the load now presents an inductive power factor equal to 0.95. In this new condition, what is the apparent power supplied by the power supply network? Okay, my friends, this is the exercise. Let's go to the solution. The exercise provided this data, okay, because it is an exam and we are forbidden from using calculators. That's why the exercise already provided the angles that we are going to work with. Let's go to the solution. It should be noted that the real or active power of the load is invariant and that the capacitive compensation only reduces the reactive power demanded from the system. Let's see the uncompensated system first. Let's work on the uncompensated system first. The exercise said that S1 is equal to 1 kVA. This is the apparent power of the load under an inductive power factor of 1 is equal to 0.76 inductive. Okay? This is the condition of the uncompensated system. Observe that the exercise already provided the angle, okay, the angle of the power factor. The angle of the power factor, 1, is the inverse cosine of the power factor, okay? The angle of the power factor is the inverse cosine of the power factor, and the exercise already gave us this angle, which is 40.536 degrees. Okay? As the power factor is inductive, the current lags the voltage by the angle of the power factor. That is, the voltage phasor has a magnitude and the angle. Let's stipulate that the angle is 0 degrees, and for the current phasor is equal to the magnitude of the current in an angle. Observe one more time that as the power factor is inductive, the current lags the voltage by the angle of the power factor, okay? That's why the angle of the current is the negative of this, meaning that the current is lagging, alright? That's why I put a negative sign here. The complex power is therefore the complex power with a dot on top is equal to S1 phase phi 1. Okay, and we already know phi 1. Phi 1 is the angle of the power factor. In other words, this can be calculated as the voltage phasor times the complex conjugate of the current phasor, okay? Which is equal to V phase 0 degrees times I phase 40.536 degrees amps. Observe that this is the actual current and this is the complex conjugate of the current. The actual current has an angle with a negative sign, and the angle of the complex conjugate of the current has positive sign. Alright? And therefore, here, as the exercise said, the complex power is going to be the apparent power 1000, okay? The apparent power 1000 in an angle, and the angle is 40.536 degrees voltampere, VA. Okay, this is the complex power fed by the system. The load demands this complex power from the system, and the apparent power is 1 kV, 1 kVA, okay? Now let's work on the uncompensated, the compensated system. We are going to compensate the system with a capacitor bank. Let's work on the compensated system now. Let's work on the compensated system now. It is going to be the complex power number 2 is going to be equal to the apparent power number 2 in a phase. We're calling it phi 2. Okay, and the exercise stated that the power factor has to be raised to 0.95. So the new power factor has to be equal to 0.95. Okay, my friends? As the exercise provided, the exercise already provided this, okay? We could not use a calculator in this exam, and to facilitate us, the exercise provided this data here. And as the exercise provided, the angle, okay, the angle phi 2 is equal to the inverse cosine of power factor 2, okay? And this is equal to 18.195 degrees. Okay, my friends? Alright, so we know that as the complex power is equal to the apparent power number 2 in the phase 18.195 degrees volt ampere. Okay? And now returning to S1, remember that S1 was equal to 1000 phase 40.536 VA. We separated the powers. We have to separate the powers, okay? S1 can also be written as 760 plus J 650 VA, okay? And as the real power must not change, okay, let me put it here. P1 is equal to 760 watts. This must not change. The real power stays the same. And this is equal to P2 as well. Alright? What is going to change is the reactive power. The real power or the active power must not change. Okay? Now let's return to... We are going to see that S2 is going to be equal to 760 because this does not change, plus JQ2. And we need to calculate Q2. Okay, P2 is equal to S2 times the cosine of the power factor 2. Thus S2 is equal to 760 watts divided by the power factor number 2, the power factor of the compensated system. And then we find an apparent power equal to 800 VA. Okay? Alright. Then we know that S2 is equal to 800 phase 18.195 degrees volt ampere. Okay? We already know this. And the reactive power of the compensated system Q2 is equal to 800 times the sine of 18.195 degrees, and this is equal to 250 VAR. Alright? Then we conclude that S2 is equal to 760 plus J 250 VA. Okay? The complex power of the compensated system is this. This is the complex power of the compensated system, and this is the reactive power of the compensated system, and this is the compensated system written in Cartesian coordinates. Okay? And the conclusion that we get, what the exercise asked from us, let me refresh my mind. The exercise in this new condition, what is the apparent power supplied by the power supply system to the load? Okay, the capacitor bank is providing part of the reactive power, and the apparent power provided by the system to the load is this 800 VA, okay? S2 is equal to 800 VA, and this is the solution of exercise number 3, my friends. Let's go to exercise number 4 now. A single-phase electrical equipment requires an apparent power of 1500 volt-ampere from a 250 phase minus 40 degrees volts voltage source under a cosine 10 degrees inductive power factor. Okay? This is the data that the exercise provided. And now the question, what is the impedance of the load? Okay, my friends, this is the question. Let's solve it. Let's go to the solution. Firstly, we are going to calculate the magnitude of the impedance. The magnitude of the impedance can be calculated as the voltage squared divided by the apparent power. Okay? This is how we can calculate the magnitude of the impedance. And then it is equal to 41.67 amps. Now let's work with the angle. The angle of the impedance is the angle of the power factor. And observe that the cosine 10 degrees is equal to the cosine of negative 10 degrees. Okay? And as the exercise stated that the load is inductive, its angle must be negative. Okay? Its angle must be negative. Then Z is equal to 41.67 in the phase negative 10 degrees ohms. Alright, my friends, this is a very easy exercise. One more time, we wanted to calculate the impedance of the load under the conditions provided by the exercise. We began by calculating the magnitude of the impedance by dividing the voltage squared by the apparent power. And how about the angle? The exercise said that the power factor is equal to the cosine of 10 degrees, okay? But as the load is inductive, the exercise stated that the load is inductive, we are not going to use cosine 10. We are going to use cosine negative 10, because the cosine of 10 is equal to the cosine of negative 10. And as the load is inductive, its angle is negative. Alright, this is all for exercise number 4. Let's go to exercise number 5. Exercise number 5, a balanced three-phase power system composed of a Y-connected three-phase source and the ACB sequence feeds a three-phase load with an inductive characteristic of 7.5 kilowatts and a power factor of 0.5. Knowing that the voltage in phase A is 250 volts and angle 20 degrees, what is the current that passes in phase B? Okay, the exercise says that the sequence here is ACB. Okay, this is the exercise number 5. Let's go to the solution. For phase A, the phase current can be calculated as phase A, the phase current can be calculated as the power divided by 3 times the voltage, the phasor voltage, the phase voltage, 3 times the phase voltage times the power factor. And this is equal to, you just substitute the values, 7.5 kilowatts divided by 3 times 250 volts times 0.5, and this is equal to 20 amps. Okay, this is for phase A. We want to calculate, the exercise wanted us to calculate the current that passes in phase B. We are almost there. We calculated for phase A first. Now let's work with the angle. The angle of the power factor is equal to the inverse cosine 0.5. Okay? The exercise said that the power factor is 0.5 lagging here, and the angle is therefore 60 degrees. Alright? Therefore, the angle of the current will be the angle of the current, the angle of the power factor is equal to the angle of the voltage minus the angle of the current. Okay, this is basic. Every electrical engineer needs to know this, that the angle of the power factor is equal to the angle of the voltage phasor minus the angle of the current phasor. And in this way, the angle of the current is equal to the angle of the voltage minus the angle of the power factor, okay? And this is equal to 20 phase, which is equal to 20 degrees minus 60 degrees, which is equal to negative 40 degrees, okay? This is for phase A. Now let's work on phase B. For phase B, bearing in mind that we are dealing with an inverse sequence ACB system, it is necessary to add 120 degrees to the angle of the current in phase A, okay? We have the phasors here, okay? This is ACB, A is here, C is here, B is here. We have to add 120 degrees, okay? Because this is the inverse sequence. All right. Thus the angle is negative 40 degrees plus 120 degrees, which is equal to 80 degrees. Okay? And the current along phase B is I. B is equal to 20 phase 80 degrees, okay, amperes. This is the current that flows along phase B. Okay, my friends, and this is all for exercise number 5. Let's go to exercise number 6 now. Exercise number 6 now. A Y-connected 3-phase electrical equipment has an apparent power of 400 kVA and is fed at 10 kV. The base power and the voltage chosen for the sector where this equipment is installed is 100 kVA and 10 kV. What is the impedance in per unit? Okay, the exercise wants us to use this data to calculate the impedance in per unit. Okay, my friends, this is what we are going to do. Let's go to the solution. The impedance of the equipment is given by, let's calculate first the impedance of the equipment. The impedance of the equipment, as we did previously, is the voltage squared divided by the apparent power, which is 400 kVA. Okay? And this gives a value of 250 volts. Alright, this is the impedance of the equipment. Now let's calculate the base impedance of the system. The base impedance of the system, ZB, is going to be the voltage squared divided by the apparent power. And this is equal to 1 kilo ohms. Okay? The base impedance of the system is 1 kilo ohms. Alright? Consequently, the value of the impedance in per unit is ZPU is going to be equal to the value. Oh, sorry, this is not in volts. Sorry, this is in ohms. Okay? Frequently I make mistakes, but sometimes I spot them and I correct them. When I can't see the mistakes that I make, please leave me a note and you will help me, okay? This is 250 ohms and this is 1 kilo ohms, okay? We simply divide to calculate the value of this impedance in per unit. We simply divide the value of the impedance, 250 ohms, by the base impedance of the system, and we find 1 k ohm, and then we find 0.25 per unit. Okay? The value of the impedance in per unit is 0.25 pu. Okay, my friends, and this is all for exercise number 6. Let's go to exercise number 7 now. Exercise number 7. The matrix presents the relationship between the electrical quantities A, B, and C with the respective symmetrical components X, Y, and Z. The question: determine the sequence of the symmetrical components. Okay, my friends, we are going to analyze this matrix equation that the exercise provided and compare it with the standard way of writing the relationship between currents and voltages with their symmetrical components. Okay, developing this, we find that A is equal to X plus Y plus Z, and B is equal to A squared times X plus A times Y plus Z, and C is equal to A times X plus A squared times Y plus Z. Okay? If we compare the aforementioned expressions with the standard way of relating electrical quantities to their symmetrical components, we find, okay, the standard way, the way we normally do is this. For example, for voltage, VA, VB, and VC is equal to 111, 1a squared a, 1a squared, VO, V1 and V2, all right? And again, if we develop, we find that VA is equal to VO plus V1 plus V2, VB is equal to VO plus A squared V1 plus A V2, and VC is equal to VO plus A V1 plus A squared V2, okay? We have to compare this with this. This is what the exercise wants us to do. Alright, if you take a look, let's take a look at Z. Let's take a look at Z. Observe that Z behaves similar to VO, alright? Okay? And what is the conclusion that we get? We conclude that Z is equivalent to the zero sequence component. Okay? Now let's take a look at X. X. For C I have AX. For C I have AV1. For B I have A squared X. For B I have A squared V1. So what is the conclusion that we get? X is equivalent to V1, is equivalent to the positive sequence component. Okay, and the last is Y. Y is equivalent to the negative sequence component. Okay, my friends, this is a question that appeared in a civil service exam here in Brazil. Okay, the exercise gave you this somewhat scrambled, and you have to write the standard way of relating electrical quantities with their symmetrical components and try to see what's going on. And we observe that Z is equivalent to the zero sequence component, X is equivalent to the positive sequence component, and Y is equivalent to the negative sequence component, my friends. And this is all for exercise 7. Let's move on to exercise 8. Exercise number 8. The inverse transformation matrix presented relates the symmetrical components with their respective phasors, considering the boundary conditions of a fault. In this way, what type of fault does this matrix present under these conditions? Okay, my friends, the exercise said that this matrix represents a fault and wants us to tell what kind of fault it is. Alright, this is the question. Let's go to the solution. Let's develop this. Okay, let's develop these multiplications and see what we get. Observe that I1 is equal to a third of, I1 is here, it is a third of 1 times 0 is 0, A times IB is AIB, and A squared times negative B is negative A squared times IB. Okay, this is for current 1. Let's do the same for current 2. I2 is equal to a third of 1 times 0 is 0. A squared times IB is A squared IB. And A times negative IB is negative AIB. And how about I3? I3 is equal to a third of 1 times 0 is 0. 1 times IB is IB, and 1 times negative IB is negative IB, and we conclude that I3 is 0, okay? And also observe here, this term is positive here, and this term is negative here. But this term that is negative here is positive here, and this term that is positive here is negative here. What can we tell about this? We observe that I2 is the negative of I1, and that I3 is 0. What does it mean? When I3 is 0, it means that the ground does not participate in the fault. Okay? According to the matrix provided by the exercise, we see that we have a phase-to-phase short circuit. Since we have two currents equal in magnitude and in opposite directions. And since I3 is 0, we observe that the ground does not participate in the short circuit. We called it I3, but we should call it I0 because I0 represents the ground better, but the exercise chose to use I3, okay? So this is a phase-to-phase short circuit, like this, phase, and here the ground. The short circuit is from one phase to the other, and the ground does not participate in the short circuit. Okay, my friends? And this is all for exercise number 8. Let's go to exercise number 9 now. Exercise number 9 now. In the analysis of a three-phase circuit through its symmetrical components, the following values for phase A were identified. Positive 10 phase 30 degrees, negative 6 phase 330 degrees, and 0 sequence 3 phase 0 degrees volts. Okay? This is the data that the exercise provided. Given the above, what is the value of the voltage of phase B? Okay, my friends, the exercise gave this information for phase A, and it wants us to find the voltage of phase B. Okay? This is the question. Let's go to the solution. The voltage at phase B can be calculated as, in accordance to Fortescue theorem, VB is equal to VB of 0 sequence plus VB of positive sequence plus VB of negative sequence. But there is a catch here. We can relate this with this, Okay? We can relate this with this. How? I'm gonna show you. VB is equal to VA0, VA of zero sequence, plus A squared times VA of positive sequence plus A times VA of negative sequence, okay? Now we can use the values, alright? In accordance to Fortescue theorem, we have this, the first expression, but there is a catch here. Using this operator here, one phase 120 degrees, we can relate VB1 with VA1, VB2 with VA2, and then we have everything to calculate what the exercise wanted. Alright, just substitute the values. VB is going to be equal to 3 phase 0 degrees volts plus 1 phase negative 120 times 10 phase 30 degrees plus 1 phase 120 degrees times 6 phase 330 degrees. Okay? We simply use the values for phase A to discover B. But there is this catch here using this operator, because we know that if the phase sequence is A, B, C, A, B, C, B is gonna lag A by 120 degrees, okay? And the C is gonna lead A by 120 degrees, okay? That's why we use these operators here, the operator A and A squared. Alright, my friends? And now it's simple mathematics. You have to learn how to deal with complex numbers, okay? And then we find that VB is equal to 3 minus J4, alright? In this way, the magnitude of VB is equal to 3 squared plus negative 4 squared, which is equal to 5, and the angle is the inverse tangent. The angle is the inverse tangent of negative 4 divided by 3, and this is equal to negative 53.1 degrees. Okay, my friends, and now with these results we have found the voltage. The voltage can be expressed in this way in the Cartesian coordinates, or you can simply use the method that I prefer, okay? The polar form, 5 phase negative 53.1 degrees volts. Okay, my friends, and this is the solution of exercise number 9. Let's go to exercise number 10 now. Exercise number 10. A single phase circuit is composed of a voltage source, EA, connected to a load through a cable of impedance Z. Under the current operating conditions, the load operates with a terminal voltage V phi and current IL. The voltages and current are listed in the table. The exercise provided us this information here, okay? And the question, given the above, what is the value of the resistance of the cable? Okay, my friends, this is the exercise. Let's go to the solution. And the exercise wants us to calculate the resistance of this cable here. Okay, before calculating the resistance, let's calculate the impedance. The impedance of the cable is Z is equal to EA minus V phi divided by IL. Okay, this is very simple. All we need to do is to substitute the values. It is 150 phase 90 degrees volts minus V phi 120 phase 0 degrees volts, and this divided by the current 10 phase 45 degrees amps. Okay, but this is in the polar form. We need to convert it to the Cartesian form. Let's do it. Z is equal to negative 120 plus J 150 divided by 5 times the square root of 2 plus J times 5 times the square root of 2. To eliminate this square root of 2 from the denominator, we are going to multiply it by 5 square root of 2 minus J 5 square root of 2 divided by 5 square root of 2 minus J 5 times 5 square root of 2. Okay? And in this way we eliminate the square root, any square from the denominator. And separating the terms, we find that the impedance is equal to 150 divided by 100 phase times the square root of 2 minus J 1350 divided by 100 times the square root of 2. Okay, this is the entire impedance. We are not interested in the entire impedance. The exercise wanted us to calculate the resistance of the cable, and the resistance of the cable is the real part of the impedance. Okay, so the resistance is equal to 150 divided by 100 phase times the square root of 2, which is equal to 1.5 times the square root of 2 ohms. Okay, my friends, this is what the exercise wanted us to calculate. It didn't want us to calculate the entire complex number, the impedance. It only wanted us to calculate the real part of the impedance, which is the resistance, and for us it is 1.5 times the square root of 2 ohms. Okay, my friends, and this is all for exercise 10. Let's go to exercise 11. Exercise number 11. The figure shows a Y-connected electric power system composed of a three-phase load of 30 kilowatts with an inductive power factor of 0.86 and a single-phase load connected to two phases with a power of 10 kilowatts and an inductive power factor of 0.5. The question: what is the total power factor of the loads? Okay, my friends, this is the exercise, and the exercise wants us to calculate the total power factor of the loads. Okay, let's go to the solution. As the exercise stated, the single-phase load has a real power equal to 10 kilowatts and an inductive power factor equal to 0.5, and the three-phase load has a real power equal to 30 kilowatts and an inductive power factor equal to 0.86. Let's work firstly on the single-phase load, and I'm going to call it load A. Load A for us is the single phase load. Okay, the apparent power of load A is equal to the real power of load A divided by the power factor of load A. Okay, substituting the values, we know that it is 10 kilowatts divided by 0.5, and this is equal to 20 kVA. this is the apparent power of load A, the single phase load. Now that we have the apparent power, we need to work on the angle. The angle theta A is equal to the inverse cosine of the power factor A, which is equal to the inverse cosine of 0.5, and this is equal to 60 degrees. Okay, with these values we can compose the complex power. The complex power with a dot on top is equal to 20 phase 60 degrees kVA, or if you prefer, it is equal to 10 plus J 17.3 kVA. Okay, now let's work on the three-phase load. We are going to call it load B. Load B is the three-phase load. One more time, the apparent power is equal to the real power divided by the power factor. The real power for us here is 30 kilowatts, and the power factor is 0.86, okay? And calculating this, we find that the apparent power is 34.89 kVA, okay? Now that we have the apparent power, we have to work on the angle. The angle theta B is equal to the inverse cosine of the power factor, and this is equal to 30.86 degrees, okay? And with the apparent power and the angle, we can compose the complex power, and the complex power of the three-phase load is equal to 34.89 in the phase 30.86 degrees kVA, or if you prefer, as B is equal to 30 plus J 17.8 kVA, okay? All we need to do now to finish the exercise is to combine the real powers and the reactive powers, okay? The total real power is gonna be 30 kilowatts plus 10 kilowatts, which is equal to 40 kilowatts, and for the reactive power it is going to be 17.8 kVAR plus 17.3 kVAR, and this is equal to 35.1 kVAR. Okay, my friends? Alright. I'm going to erase here because I'm gonna need more space. Okay? I'm going to write the final result here. And then we know that the total apparent power is equal to the total complex power, not the total apparent power. The total complex power is going to be 40 plus J 35.1 kVA, which can be also be written as 53.22 phase 41.4 27 degrees kVA. Alright, what we wish is to calculate the cosine of the angle of the total complex power. The cosine theta total is equal to the cosine of 41.27 degrees, and the theta total is equal to no, this is the angle. This is the angle, okay? Theta total is this, the angle. Theta total, okay, the combined angle is this. What we wish is the cosine of this. We wish the cosine of theta total, which is equal to the cosine of 41.27 degrees. Okay, and this is equal to 0.75. Okay, my friends, this is the solution of this exercise. The exercise wanted us to calculate the total power factor of the loads. We began by expressing load 1 in its complex form, the complex power of load 1, and we did the same for load B. We expressed it in the complex form, the complex power of load B. We summed the real power and we summed the reactive power, and we got the complex number here, the total complex power drawn from both loads at the same time. And we got this angle here, okay? The cosine of this angle is the combined power factor. Okay, my friends? And this is all for exercise 11. Let's go to exercise 12. Now, my friends, we are going to solve an exercise very similar to exercise 1, exercise number 12. In a power system, an electrical equipment has nominal power and voltage values of 20 MVA and 100 kV respectively. The bases in the region where this equipment is installed are 50 MVA and 50 kV. Knowing that the reactance of this equipment at its nominal values is 0.04 pu, what is the new value of its reactance under the new basis? Okay? In exercise 1, you return to exercise 1, in which I demonstrated how we get to the final expression to convert from one system to another. Here we are going to use only the final expression, okay? Back then we understood that X pu B2 is equal to X pu B1 times VB1 over VB2 squared times SB2 divided by SB1. Okay? I demonstrated how to arrive at this expression in exercise 1. You can return to see how it arises, alright? Using the values provided by the exercise, we find that X pu B2 is equal to 0.04, okay? The old value times 100 kV divided by 50 kV squared times 50 MVA divided by 20 MVA, and this is equal to 0.4 pu. Okay? The old value of the reactance is this. VB1 is 100 kV, VB2 is 50 kV, SB2 is 50 MVA, and SB1 is 20 MVA, and the value that we were looking for is 0.4 pu. Okay, Under the nominal values, the value of the reactance is 0.04 pu, but when we install this equipment in this system having these base values, the value of the reactance is 0.4 pu. Okay, my friends, and this is all for exercise 12. Let's go to exercise 13. Exercise number 13 now. In a distribution system, a single phase to ground short circuit occurred. The bases at the default location are equal to 10 kVA and 1 kV. And the pre-fault voltage was equal to 500 volts. Knowing that the sum of the positive, negative, and zero sequence resistances is 50 ohms, what is the fault current in per unit? Okay, my friends, this is the question. Let's go to the solution. Firstly, we need to understand that this is a single phase to ground short circuit. Okay? And the bases at the region the short circuit occurred was 10 kVA and 1 kV. And the pre-fault voltage was 500 volts. Okay, my friends? These are the sequence networks that we use to model short circuits. Depending on the short circuit, we are going to connect them in a different way. For example, for a three-phase short circuit, we use only the positive sequence. But as it is a single phase to ground short circuit, we are going to have to use the three. Alright? And they are connected in this way. Z1, Z2, and Z0, and here, as there is a short circuit, we have to connect this because of the short circuit, okay? There is going to be a current here of the positive sequence, a current here of the negative sequence, and a current here of the zero sequence. And this is E1. I'm going to call this current here simply I. You have to bear in mind that I is equal to I1, which is equal to I2, which is equal to I0, okay? And the resistances Z1 plus Z2 plus Z0, they are the total Z total. I'm gonna call them Z total, okay? And we need to find the value of the current. The value of the current is gonna be equal to E1, which is E1 divided by the value of Z total, and this is equal to 500 volts divided by 50 ohms, and this is equal to 10 amps, okay? 10 amps. But these are the symmetrical components, okay? These are the symmetrical components. IA is equal to the symmetrical component of positive sequence plus the symmetrical component of negative sequence plus the symmetrical component of zero sequence, and this is equal to, as they are equal, 3 times I. Then the current along the cable is going to be equal to 3 times 10 amps, which is 30 amps. Alright? This is the current along the cable at the time of the short circuit, 30 amps. We have to convert this value here from amps to per unit as the exercise requested. The exercise asked, what is the fault current in per unit? To convert it to per unit, we have to establish a base. Okay, so I base is equal to the base apparent power divided by the base voltage, okay? And we use the values that the exercise provided, and it is 10 kVA divided by 1 kV, okay? And this is equal to 10 amps. And the value of the current in per unit is simply IPU is equal to IA divided by I base. And this is equal to 30 amps divided by 10 amps, which is equal to 3 PU. Okay, my friends, this is the answer. This is the solution of the exercise. This is all for exercise 13, my friends. Let's go to exercise 14 now. Exercise number 14 now, my friends. For the circuit of the figure, calculate the current in phase C. Okay, my friends, this is what the exercise wants. The exercise wants us to calculate the current in phase C, okay? And the exercise provides this data here, saying that the value of the impedance is 20 phase 15 degrees ohms. The value of the line voltage between line A and line B, VAB, is 220 phase negative 5 degrees volts, and it is an inverse sequence. Okay, this is the inverse sequence ACB. Alright, as it is the inverse sequence, C lags A by 120 degrees. Okay, being this an ACB system, we see that the VAB, VBC and VCA will be equal to 220 here phase negative 5 degrees as the exercise said, and as VBC leads VAB, it is going to be 115 degrees, and as VCA lags VAB by 120 degrees, the angle here is going to be negative 125 degrees, okay? These are the line voltages, but before we calculate anything, we need to convert from line voltages to phase voltages, and I'm going to explain to you how we can do this. Take VCN, for example. VCA is equal to VCN minus VAN, alright? Which can be expressed as V phi phase negative 120 degrees minus V phi phase 0 degrees, okay? Don't worry much about the angle of VAN, because here I just want to explain to you how to convert from line voltages to phase voltages. This is not important. What's most important is that C lags A by 120 degrees. That's why I put negative 120 degrees here. When I finish calculating this, you are going to understand the purpose, alright? So, VCA is going to be equal to V phi multiplying the cosine of negative 120 degrees plus J times the sine of negative 120 degrees minus V phi, okay? And if we carry out this, we find that VCA is equal to negative 1.5 minus J 0.87 times V phi, which is equal to the V phi times the square root of 3 phase negative 30 degrees, okay? It is negative 30 degrees because this is the inverse sequence. Had it been the direct sequence, this sign here would have been positive. Okay, my friends, this is how we convert. Taking from here, VCA is equal to 220 phase negative 125 degrees. And we want VCN. VCN is going to be equal to 220 phase negative 125 degrees divided by this, the conversion factor, which is the square root of 3 times in the phase negative 30 degrees. Okay? And in this way, VCN is equal to 127 phase negative 95 degrees volts. Okay? Ultimately, we can find the current IC because this is what the exercise wanted us to calculate, the value of IC. IC is equal to VCN divided by the value of the impedance, and then it is equal to 127 phase negative 95 degrees divided by 20 phase 15 degrees, and this is equal to 6.35 phase 80 degrees. Okay, my friends? No, negative 95, this is positive, I put negative, and it is 90, 110, negative 110 degrees. Okay, my friends, this is the value of the current in phase C, and this is all the exercise wanted us to calculate. Let's go to the last exercise, my friends. Let's go to exercise 15. A 50 kVA load with a lagging power factor equal to 0.9 is connected to a bus. Calculate the reactive power a capacitor bank will need to provide to raise the power factor to 0.92 lagging. Okay, my friends, this is the exercise. The exercise wants us to calculate the reactive power a capacitor bank will need to provide to raise the power factor to 0.2 lagging. And the exercise provided this information here, okay, for the uncompensated system, 50 kVA and 0.9 lagging power factor, and the desired power factor is 0.92. The exercise also gave this because in this exam you could not use a calculator. Then the exercise gave this information to facilitate your calculation. Alright, my friends, let's go to the solution. Let's work on the uncompensated system first. I'm gonna call the apparent power of the uncompensated system as S1, which is equal to 50 kVA. Alright, and the power factor of the uncompensated system is 0.9. Alright, and if we go to the table, we see that the inverse cosine theta 1, the inverse cosine of 0.9 is equal to 26 degrees. Okay, with the apparent power and the angle, we have the complex power. The complex power of the uncompensated system is 50 phase 26 degrees kVA. Alright, this is the uncompensated system. Let's split this. Because we are going to need to know the constituent parts of this complex power, and they are 44.94 plus J 21.92 kVA. Okay, this is the uncompensated system. Let's work on the compensated system now. The first thing that we need to notice is that P1 has to be equal to P2 because the real power must not change. Okay, the real power must not change. What's going to change is the reactive power, alright? So it is equal to 44.94 kilowatts. This number here must not change, alright? And it was given that the desired power factor is 0.92. Okay, the power factor number 2 is equal to 0.92, and the exercise already gave you the angle. The inverse cosine of 0.92 is 23 degrees. Then phi 2 is equal to the inverse cosine of 0.92, which is equal to 23 degrees. Okay, with the angle, no. We still have to do something here. We have to calculate the apparent power. The apparent power 2 is going to be equal to P2 divided by the power factor number 2. And this is going to be equal to 44.94 kilowatts divided by the new power factor, which is 0.92, and the apparent power is equal to 48.85 kVA. And in this way, we have the complex power of the compensated system. The complex power of the compensated system with a dot on top is equal to the apparent power 48.85 in the phase of 23 degrees kVA. Okay? Alright? And this is the complex power of the compensated system. And if we split this, we have that as 2 is equal to 44.94 plus J 19.1 kVA. Observe that the real power is the same for the compensated system and the uncompensated system, but the reactive power changed. This was 21.92 and this is 19.1, okay? The variation in reactive power is delta Q. The variation in reactive power is Q1 minus Q2, and this is equal to 21.92 minus 19.1, and this is equal to 2.82 kVAR. Alright? And what is the conclusion that we get? Therefore, the capacitor bank will need to supply 2.82 kVAR of reactive power. Okay, my friends, the exercise asked us this. Calculate the reactive power a capacitor bank will need to provide to raise the power factor to 0.92 lagging. And this is the amount of reactive power that the capacitor bank will need to supply to raise the power factor from 0.9 to 0.92. Okay, my friends, this is the video that I wanted to make. I hope you enjoyed it and learned from it. I am a teacher, guys. If you want to book a lesson with me, use my WhatsApp number. Goodbye!